Stanford University.
Thank you, Sally. It's nice to be here to talk to you about this, which does seem to be in the news almost every day. And the reason is principally because it's become common knowledge now that the sheer volume of natural gas that can be extracted from organic rich shale formations is truly enormous. In North America alone, there's something on the order of about 100 years supply of natural gas at current consumption rates. It's coming from areas all around the country and in Canada, as you can see. And the technology to extract this gas from these extremely low permeability formations, which I'll talk about later, is now being applied to low-quality oil reservoirs. So where these areas are shaded green, it means not natural gas being extracted from shale, but actually gas and oil or just oil. So this technology, which I'm about to tell you about, has sort of revolutionized the energy picture in North America by making a known source of energy available to us in extremely large quantities. And it's truly daunting that in the next decade or so, tens of thousands of wells are likely to be drilled, maybe 1 million hydrofracks carried out. And so it's really pressing to address two major questions. One is, how do we optimize the development of this resource in the most intelligent way possible? And how do we minimize the environmental impact? Now, this is not just happening in the United States. Last spring, the Department of Energy released a global assessment. There were many areas shown in gray for which there was no data available, but from the areas that were, from which data was available, there was something like 100 plus years of natural gas globally. It's less, the fraction of it coming from shale is less because of the large conventional gas deposits in the Middle East and Russia, but nonetheless, the resources are enormous. And no sooner had this report been published than major new assessments in Argentina, the UK, and even in Bengal province in India. So it's really having a big impact. Now, this is a slide I borrowed from Sally, and I like to show it to scare students. So the first way I scare them is by mid-century, when they are about the age that I am now, that kind of frightens them, the challenge is not only to address the energy and environment issue that many of us are struggling with every day, but to do that in a context that allows us to provide roughly twice as much energy as we currently use. So not only do we have to address this issue of economy, national security, environment, and society, kind of we're all very familiar with the complex interaction of these many questions. We have to increase the amount of energy that's available to sustain the growing economies of the world's population. And it's truly formidable challenges. Now, natural gas has a few really large advantages over conventional fossil fuels. And the most important thing, I think, is to compare natural gas with coal, because the opportunity to replace coal with natural gas for electrical power generation is right before us. This is low-hanging fruit, and we literally can cut our CO2 emissions coming from burning coal in half. And that's what this slide from the DOE shows, that the CO2 emissions are approximately 50%. And of course, things like particulates, mercury, the sulfur and nitrogen oxides, natural gas is a far cleaner fuel than coal. In fact, the only reason we use coal at all is because it appears to be cheap and it's abundant. And now we have a logical alternative. Bert Richter showed this slide last week, and it has to do with the life cycle analysis, the full cycle of using natural gas as a fuel. And this study, which is about 10 years old now, does show that the life cycle analysis for natural gas emits half as much CO2 as coal. Now, there's been some question about the life cycle analysis, and there are open issues, but the Department of Energy and a number of other responsible studies are coming down more or less at this picture that we emit about half as much CO2 as using coal. So as I have become more and more enthusiastic about natural gas and have worked on it more and more over the past few years, it's not that I'm trying to maintain the era of fossil fuel. We have to decarbonize our energy system. There's simply no question about it. But natural gas provides a wonderful bridge between now and, say, 2050, by the time we have, a large enough portfolio of renewables and alternatives to completely get away from fossil fuels, far more so than we can today. So I see natural gas as the bridge fuel to a decarbonized future, not as a way of, sustaining business as usual. Now, in its report in 2009, America's Energy Future, the National Academy did a cost analysis for making electricity with different forms of energy. And when they used the low price of natural gas, which was $6 per million BTU, which is twice its current price, natural gas was cheaper than coal. So there's really no economic impediment. It's cheaper today to use natural gas. In fact, the current price of natural gas it's so cheap that companies can hardly drill and produce it profitably. So natural gas beats coal, and it beats coal even more once we consider the cost of carbon capture and storage. And this cost, especially for coal, keeps creeping up, and the differential is growing, and you're generating half as much CO2 to begin with. So let me talk something about the technology and what's made all of this possible. This is a slide that shows both the total gas production and the number of wells drilled in the Barnett Shale. The Barnett Shale is the Fort Worth Basin, the Dallas-Fort Worth area of north central Texas. And a very stubborn oil man by the name of George Mitchell really kept at it for years and years and years, and he and his company finally kind of unlocked the methodology to get the gas out. Now, originally they were drilling vertical wells and making large hydraulic fractures as shown, and that's good. The hydraulic fracture is a permeable conduit in contact with over a large area with relatively impermeable rock, and production was increased. Then the technology for horizontal drilling came along, and they would drill a long well in the direction of the maximum compressive stress in the earth, and they would get a long hydraulic fracture like that. And that was better, but still they weren't producing commercial quantities of gas. And then they turned the direction of the well and drilled in the direction of the minimum horizontal compression in the earth, and started to make a succession of hydraulic fractures along the length of the well. And this is really a big part of the secret, that they're able to dramatically increase the permeability of the shale and produce gas in quantities that were economically significant. Now, there's another subtle difference in the technology, and that is they began to use essentially clear water to do the hydraulic fracturing. Now, hydraulic fracturing has been around for about 60 years, and traditionally, like when this kind of fracking was done, they'd use a very complex gel that had very high viscosity in order to carry sand as far from the well as possible to prop open this fracture. And that would allow this area of contact to be large and a very permeable fracture plane to exist in order for the gas to flow into the well. With slick water, as it's called slick water because a little bit of a friction reducer is added along with some biocide and a very little thickening agent. What's actually happening is by design, or by happenstance, depending on who you ask, what's happening is the permeability of the shales, while being low, is enhanced by pre-existing natural fractures. And so the water that's used in the hydraulic fractures is actually seeping into the pre-existing fractures and inducing tiny little microseismic events. You can think about these as extremely small little earthquakes. And the slippage, the very small slippage on these faults is actually changing the permeability of the shale, or at least that's what is thought. And so we get hundreds and hundreds of these microseismic events, and we are literally changing the permeability of the shale and allowing the gas to flow more evenly, more smoothly, and in larger quantities. So it's a very different technology than this, because in this case you're just creating this permeable plane, and in this case you're actually changing the volume of the rock and enhancing its permeability. Now, at the time we got involved in this about 4 or 5 years ago, they were drilling thousands of wells per year, about 10 hydrofracks, tens of thousands of these hydrofracks, and the companies were going as absolutely fast as they could. Gas prices were high, operations were profitable, and they were out drilling and operating mostly in the Barnett Shale as fast as they could. And yet, a conference of the engineers charged with this task, the Society of Petroleum Engineers, when asked, I am confident that I understand reservoir drainage, 80% said, no, I'm not confident. I am confident in our estimated ultimate recovery, 80% said, no, I'm not confident. I think new completion technology is needed, 85% said yes. So in the middle of this kind of rush to develop the resource using this kind of standard technology, which was profitable, when asked, the people involved freely admitted that they didn't understand what they were doing as much as they would like in order to optimize the resource and reduce the environmental impact. And so my students and I have been engaged in this endeavor to address both of those problems for the last 4 or 5 years. And what I want to do now is talk a little bit about some of the research that we're doing. So a little bit about the rock properties. These shales are they're markedly different from basin to basin, and sometimes different within the basin. So how do the rocks themselves affect the success? What's the importance of aseismic deformation? In other words, I showed you these little micro-earthquakes. By the way, those micro-earthquakes release as much energy as a gallon of milk falling off a kitchen counter. I mean, these are very, very small events. Magnitude -2, -3 events. It's a fault patch about this big. It slips less than 1/10 of a millimeter. Very, very small events. And what we're beginning to suspect is that faults are actually moving slowly and quietly during this process and enhancing the reservoir permeability. What factors affect ultimate recovery? In other words, how do we drill fewer wells and get more gas? And how do we minimize the environmental impact? So this is a typical kind of operation. This is the Barnett Shale. These are 5 horizontal wells. Each is about 4,500 feet long. They're 500 feet apart. Each well was hydraulically fractured 10 times along its length. And the dots represent the microearthquakes that we recorded during the fracturing process. And the first question is, how do the properties of the shale affect the outcome? And you can see from the microearthquakes alone that even though the fracturing was done very regularly and very similarly, there are areas where there are hardly any microearthquakes and other areas where there are quite a few. So apparently, by doing the same thing, the shale responded quite differently. Why is that, and how does it affect productivity? I might also point out that while the Barnett Shale has been extremely successful, the Haynesville Shale, the Eagleford Shale, the Marcellus here in the Northeast, all of these shales have been great successes in the sense that the companies are employing this technology, producing commercial quantities of gas. One place, the Floyd Shale, has been kind of a bust. They drilled wells, they carried out the hydraulic fracturing, and it was completely unsuccessful. So keep that in mind. Now, we're working with organic rich shales in our lab from many different places. We sort of subdivide them into sort of high clay, which we call dark samples, or low clay, light samples. So the Barnett, the Haynesville, which is Louisiana and East Texas. Fort St. John is in Canada. The Eagleford is South Texas. And This is the work of Hiroki Sone, one of my students, and one thing Hiroki has been doing is studying how the samples creep. In other words, when you apply a force to them, they behave semi-elastically, but they keep deforming as a function of time, viscoplastic creep. And one thing that affects the creep is the amount of clay. And these samples all have a lot of clay, but when the clay gets up to be about 40%, there's so much clay that the clay is actually supporting the applied load, and the creep is greatly accelerated. And you can see that here, this 39% clay sample is creeping. In other words, it's deforming as a function of time under a constant load far more than the other samples. And what happens when a sample has this behavior of creep with time is that the stresses relax with time. So in other words, the stresses just sort of flow away over time. And so the rock is not brittle and is not amenable either to hydraulic fracturing or stimulating slip on these pre-existing faults. So a large amount of clay is really a bad thing for actually employing this technology. And it actually turns out that when you compare a lot of these shale basins, the Floyd stands out because of the very large volume of clay. So as we look at this resource on a global basis, we have to remember that we're not going to be able to simply do what we did in the Barnett and have it succeed in the same way. Methodologies will have to be developed and adapted for the geologic conditions that exist in these different places. Now, all of those little dots represent these very tiny microearthquakes that I told you about. But in fact, if you assume that each of those microearthquakes completely pulverizes the rock in their near vicinity, which makes no sense at all. We can't replicate that theoretically. But if it did, and you were able to collect all the gas from each of those small volumes, you could still only account for about 1% of the gas production from these wells. So something else has to be going on during the stimulation process. And my student Indrajit Das and I have been looking at very strange seismic signals coming from the areas that are being stimulated hydraulically, which we interpret to be slow slip on faults. In fact, when you look at the seismograms that we are recording during these operations, they look a lot like a phenomenon known as episodic tremor and slip, which is observed on deep subduction zones in the San Andreas Fault at great depth, which when these things are observed by earthquake seismologists, they are interpreted to be slow slip-on faults, and we are seeing the exact same thing in the Barnett Shale when it's being hydraulically stimulated. Now, we're trying to understand how this all fits together, and this is a model developed by Mark McClure, a student who's working with me, and Professor Roland Horn in the ERE department. And what Mark has done here is he's developed a computer model of what's going on in that group of wells that I showed. And so there's the middle well. There are several of the hydrofracts, and all those blue lines represent the natural fractures that exist in the formation, before anything is done. They're just naturally existing. They were studied actually by a certain type of imaging tool that was run in the well. So the orientation data, the density is well constrained, but they've been extrapolated mathematically through the volume. And then these wells are hydraulically fractured, and as the fractures turn from blue to red, that means that what happened is the fluid penetrated the fractures, as I described, the fractures slipped, the fractures increased their permeability, and now what you see is that the area of contact between the hydraulic fracture and this very low permeability shale is greatly enhanced by all this fault slippage. And you can see that there are areas where there's been a lot of fault slippage and a lot of permeability enhancement, and other areas that are hardly touched at all. And this kind of modeling could actually be done before the hydraulic fracturing is done, and you could in fact optimize what you do depending on the conditions rather than going out and doing everything the same in every well, as is commonly the case. Now, one of the big questions is how much gas is going to be coming out of these wells over time. And of course, the way petroleum engineers deal with this is they build mathematical models, they compare them to known fields to test those models, and the more they can test their models, the better they can make predictions. The problem here, of course, is that these wells have been under production for such a short period of time that we don't have much of a historical precedent to calibrate models. Now here are wells in the Barnett Shale, and what Peter Valco and John Lee did is they took all of the wells that were drilled in July of 2004 in the Barnett Shale, and they averaged them to get the average monthly production. And they did this because on a well-to-well basis, there's a lot of variability. So this is the average production. For the wells drilled in July of 2005, the production increased markedly. This is industry sort of getting smarter, okay, getting more well calibrated on how to optimize the drilling and fracking process to get more gas out. Between 2005 and 2006, there were still further improvements. So this is sort of a learning as you go. Now, as Valco and Lee studied these data, the initial decline could be matched very nicely with sort of conventional petroleum engineering formulas and procedures. So everything was just fine. The wells, you're producing gas, the pressures are depleting, the rate at which gas is being produced is decreasing with time. But what they couldn't predict is the fact that this production is flattening off. And in fact, there are people in the industry who are claiming that there's going to be relatively constant production for maybe 25, 30 years. And of course, that means that while the gas rate is low, these wells are going to be producing gas for a very long period of time. And we'll see. Now, one reason it's complicated and hard to know whether such claims are valid is that what's happening at very fine scales within the shales is very poorly known, and we're just beginning to get sort of an inkling of the pore structure. So this is an SEM photograph showing a piece of kerogen. That's the organic waxy substance from which the gas is coming. So the bedding planes are left to right in this picture of the Eagle Ford Shale from South Texas. As we zoom in, you can start to see structure within the shale, okay, and you can start to see some of the pores. And there are the pores right there, about 50 to 100 nanometers across. Very, very small pores. And this is where the gas is originating. And the question of how the gas actually gets out of the shale is a very good one, and we're just beginning to understand it. My student Arjun Kohli, who made these photomicrographs, has just returned from Poland, and I want to show you some really cool images he just brought back over the weekend. Now, I've said repeatedly that the permeability of these shales is very low, or very, very low. This shows permeability as a function of sort of the pressure that's acting on the shales, and they start about 140, 150 nanodarcies, and as the pressure increases, the permeability drops by about a factor of 2. So what do these numbers mean? Well, 100 nanodarcies is 1,000,000 times smaller than a conventional gas reservoir. So if we think about sort of the gas industry, drilling wells, producing gas as it has for 100 or more years, 100 millidarcies is kind of an average number for a permeability. So we're trying to produce gas from a material that's 1,000,000 times less permeable than a conventional reservoir. And that's the challenge. That's why this horizontal drilling, multi-stage fracturing is needed. And that's why the mystery of how this fluid flow occurs is so profound. Now these are, it's a little hard to see with this bright light. If the lights could be dimmed, if anyone's, thank you. So these are nano CT scans. The scale over here is that's about 0.5 millimeter. And what you're seeing is the bedding planes from left to right. And what's shown in green on the left is the kerogen, which is distributed through the sample. And in red is the porosity, and they're superimposed. And you can see the similarity between the green and the red. In other words, the pores are in the kerogen. And somehow at this nano scale, this has all got to link up in order for the gas to flow out of the kerogen through microcracks into larger scale fractures and so on, and actually make its way out of the samples. And we don't exactly know how that happens, and it could well be different in every one of these shale basins that I showed you about. And in addition, when we start to talk about flow at these nano scales, it's not the kind of flow we're used to talking about. Petroleum engineers, hydrologists talk about Darcy flow. You apply a pressure gradient and the fluid will flow with a certain rate according to the permeability. Okay, very simple, very well understood. But as we get to these smaller and smaller scales, the mechanisms by which flow is occurring is changing, and processes such as diffusion and desorption start to become very, very important. And so there's a change in the flow mechanism, and what we're beginning to suspect is what's happening as these curves flatten is that we're starting to see the desorption of gas that's adsorbed to the clay and adsorbed to the gas molecules, absorbed to the clay and adsorbed to the organics, is desorbing and starting to flow and contributing to the production. We're trying to model that right now, but even if it is true, we still haven't addressed the question about how long production will persist, and this is the problem we're working on. So despite the fact that this is a resource of sort of global strategic importance, despite the fact that we have a basic methodology that works, there's just hundreds of fundamental questions we still don't understand, and it's going to take years for scientists and engineers literally around the world to work at the issue of optimizing the resource development. You know, recovering 25% of the natural gas, which is more or less the metric today, is really criminal, leaving 75% of the gas behind. If you could have the same number of wells, exert the same, effort, and get half the gas, you'd be doing twice as good. So it's really important to try to have a better understanding of what's going on and to optimize recovery. At the same time, everyone in the room is very aware of all of the environmental issues that have arisen associated with shale gas development. There have been cases in which surface contamination has occurred due to spills or other practices around well sites. There's been gas leakage from wells that have been quite serious. There are issues associated with the disposal of flowback waters. After you make the hydrofracks, inject all this water, you flow back the water. The water comes back. You basically inject clean water with relatively few chemicals, but what comes back is highly saline, has arsenic, selenium, iron in it, so you have to do something with this flowback water. There's a real concern that hydraulic fracturing can affect well water and surface aquifer supplies. There's some earthquake triggering associated with injection of flowback water. And there's a big impact on residents and the local land system. And all of this is summarized by no fracking. No fracking, no fracking. I really hate the word fracking, but that's just my... And the issue is not what words are used, but if you misidentify the problem, you misidentify the solutions. And there are real problems, and they have real solutions, and we have to work to find these solutions and apply those solutions and minimize the environmental impact. And just saying no fracking does a disservice to what the challenge really is. And the DOE committee that Sally referred to has issued 2 90-day reports. We're finished with our task. This was the first, and the second report came out in November. The committee was chaired by John Deutsch. There were 7 of us, and it was a highly diverse committee. Dan Yergin is known to many of you as an energy analyst, just completed the book, The Quest. Steve Holditch is the chairman of petroleum engineering at Texas A&M, and Fred Krupp is the president of the Environmental Defense Fund. So we came at this with many different perspectives, and we came up with 20 recommendations about which we all strongly agreed. And that's what I want to talk to you about. Now, our charge, delivered by Secretary Chu, literally came from the president's energy position last March, And that was to our charge was to develop within 6 months consensus recommended advice to the agencies on practices for shale gas extraction to ensure the protection of public health and the environment. And so in this 6-month period, what we did is we looked at the entirety of the issues surrounding shale gas. And we affirmed that it was in fact extremely important to the energy security of the country, that natural gas from shale is accounting for now over 30% of the total natural gas production. It's in generally had a very large positive economic impact on local communities, creates jobs, and that it can be developed in an environmentally responsible manner. That doesn't say that it is always being developed in an environmentally responsible manner, but that it could be. And we made these 20 recommendations to basically go from where we are to where we want to get, and that is to a development system that really does minimize its environmental impact. So let me talk about some of these 20 recommendations. Okay, and the first, concerning water quality, is the disclosure of the composition and flow of water at every stage of the operation. There's a lot of suspicion about the chemicals used in hydraulic fracturing. They're really pretty benign, but why talk about it? Just publish all the data. There's a lot of concern about the water that flows back. It's not nearly as benign, but let's put all the data on publicly available websites. What's in the water and what happens to the water. Okay, let's just get rid of all this sort of secrecy. With respect to hydraulic fracturing, the basic concern is that the hydraulic fracturing that typically occurs at depths averaging about 7,000 feet is that the hydrofracks are going to grow up and affect the water that's being used by near-surface wells. That's the public's concern. And in fact, in nearly all shale gas plays, there is really no issue. Now, if the shale gas is being developed at a very shallow depth, what I'm about to say is not relevant. If the shale is at a very shallow depth and very close to water supplies, you need to be extremely careful, and it may be impossible to develop shale gas resources because of the potential for contamination in some places. But in the places I've been talking about, there's really a tremendous separation between the depth of the shales and the depth of water supplies. Now, this and the graph that follows basically makes that point. Now, this is the Barnett Shale, and it's basically a plot which along the x-axis, the depth of the shale is ordered by increasing depth. So in other words, the wells throughout the basin are just resorted so that on the right we see the Barnett Shale at its shallowest depth, about 4,700 feet, typical depths 6,000 to 7,000 feet, and at the very deepest, the Barnett Shale gets about 8,500 feet within the Fort Worth Basin. Okay? Now, the water wells in the area are shown here from a USGS database, and then what this spiky signal is the depth of the shallowest and the deepest micro-earthquake that's associated with the hydraulic fracturing. So sometimes you can see there's appreciable growth of the hydraulic fracture, but we are never within more than about 4,000 feet of the water supplies. So the hydraulic fractures are not growing up anywhere close to the water supplies. In fact, the problem in the Barnett is that sometimes the hydraulic fractures grow down into what's called the Ellenberger, which is a big saline aquifer, and the operators inadvertently turn a gas well into a salt water well. And so this is the big problem. So do you get vertical growth? Yes. Vertical growth is actually a bad thing. Operators try to reduce it because you obviously want to stimulate the permeability in the Barnett, not the overlying or underlying formations. But there's no evidence whatsoever that there's any vertical fracture growth anywhere close to the aquifers, nor has there ever been a documented case in which hydraulic fracturing itself has affected a water supply. This is the Marcellus in the northeast, far fewer data points. There were something like 2,000 wells in the previous graph. There's a couple hundred here. The problem here is that there's a lot of vertical growth of the fractures, which is a waste of energy, a waste of money. But again, we have at least 3,000 or 4,000 feet between the shallowest microseismic event and the deepest well. And again, there's never been a documented case in which hydraulic fracturing fluid has reached an aquifer. So as long as the shale is deep, things are okay. But as I said before, if the shales were very shallow, you might not be able to develop the shale because of the potential for surface contamination, and that would be the end of the story. What the real issue is with protecting water quality is well construction. And doing a good job of drilling the well, casing the well, cementing the well, testing the cementing, fixing badly cemented wells before you proceed. A badly cased and cemented well can leak gas whether you hydraulically fracture it or not. And this is, it's very, very mundane, but this is the heart of the issue, especially with low gas prices, where there are lots of incentives for operators to go as fast as they can and try to cut corners. Now, this is from a paper by George King. George King is a petroleum engineer who works for the Apache Corporation. He's literally done thousands of hydraulic fractures, and it's sort of a long paper that he's written on various aspects of the problem. And he recognizes it and states the situation extremely clearly. So here's a vertical well drilling through various strata, turning horizontally in the shale. The question is, where do you set the steel casing and where do you put the cement? Economically, you want to set as little casing and do as little cementing as possible. But in fact, if you've cemented casing up here and you've not, say, cemented the section of casing here, that if you've got a coal seam or if you've got minor gas production from the shales, the only protection from this gas leaking out is the cement behind this casing, right near the surface. So there's a single barrier, and any mistake up here will allow the gas to leak out. And what George points out is that depending on the local geology, it would have been much better to put deeper casing and more cement and seal off with multiple barriers some of these other gas-producing horizons. If these wells are going to last 25 or 30 years, they can't leak for 25 or 30 years. And the money has to be spent to do it right, and the regulators have to know how to do it right and insist that it is done right from the beginning. So the three keys to really protecting the water system, to really ensuring the integrity of these wells for the next 30 years are well construction, and well construction, and it has to be adapted to the local geology. Now, this is a picture our committee took during a field trip to Western Pennsylvania, and the company involved, Range Resources, was very proud of the fact that they, in fact, ran a lot of casing, and they adapted their plans for the local geologic conditions and had multiple barriers to gas leaks, and it was really a model of what should be done. But not all the operators are following this, the regulators are not insisting on it, and it needs to be done. So well construction, and match best practice and regulation to the local geologic conditions. The water issues are really complicated depending on where you are. If you're in South Texas, just getting fresh water after the big drought last summer is a big problem. If you're in the Marcellus, having a place to dispose of the water is a big problem. Okay? If you're in Horn River, northern British Columbia, there's no infrastructure at all. You're really in a very remote frontier area. And these issues are changing rapidly. 3 years ago in Western Pennsylvania, if you told the operators that they had to recycle the water that they were using for hydraulic fracturing, they'd have told you were crazy, they couldn't operate this way, they couldn't make any money, it was just too difficult and too complicated, and every one of them is doing it today. There's no alternative. So from an economic point of view and an environmental point of view, the smart thing to do is recycle the water, and that's what they're doing. This is a 15-acre pond, which has multiple linings of plastic to prevent penetration into the ground, all sorts of bird netting and protections against wildlife getting in. They bring all the frack water here, and then they pump it out, treat it, and then reuse it. So they're reusing saline water for hydraulic fracturing. It cuts down on the amount of water and eliminates the disposal problem. This is another slide from George King. This is Horn River. So they're drilling on this pad. They're drilling 8 wells. I think there were something like 150 hydrofracks. There are basically no wells, no source of water. So they drilled 4 wells into a saline aquifer, used saline water for hydraulic fracturing, and put the flowback water back into these saline formations, and everything was fine. Not an ounce of fresh water, no salt water disposal. So the systems that have been used, that have been very water intensive and have created this big problem with disposal, they're not written in stone, and there are modifications to standard operations all the time that can improve things. One of the big issues of the last couple years have been earthquakes triggered by fluid injection. In 2009, there were a series of earthquakes in the Dallas-Fort Worth airport. Last spring, there were some earthquakes in Arkansas, which I'll talk more about in a moment. There's been a big increase in seismicity in the last couple of years in Oklahoma. And on Christmas Eve and New Year's Eve, there were earthquakes associated with an injection well near Youngstown, Ohio. So still one more environmental problem associated with shale gas development. It's important to keep the scale of the problem, so to speak, in mind. This is a plot a student helped me make. Earthquake magnitude is shown here, the size of the fault that slips here, and the amount of slip on the fault shown by these lines, and the stress drop, how much stress is relieved in the earthquake, is between these 2 dashed lines. So what does this mean? It means these little tiny microseismic events, -2, or a fault less than 1 meter in size, it slips less than 1/10 of a millimeter. So these are these firecrackers that I talked about before. They're hardly worth noting. During hydraulic fracturing in England, a magnitude 2.3 earthquake occurred. This has a scale on the order of 100 meters or so, and the slip is on the order of about 1 millimeter. Still pretty darn small. A magnitude 2.3 earthquake would rarely be felt at the surface. So most of the events that we're talking about are extremely small and pose no hazard. By the time you get to an event of the size of the one that happened in Arkansas, which is a 4.7, you're talking about a more sizable event, an event that's felt over a large area, and an event that affects a fault several kilometers in size and produces a slip of centimeter or several centimeters. So, you really want to prevent this. This is a nuisance of little consequence, and this is hardly worth talking about, but we really don't want this to happen at all. You don't want injection to induce earthquakes at any scale, in this case when we're hydraulically fracturing or when we're disposing of fluid. And that's a hard thing to do, because for most of my career, looking at seismicity and intraplate areas and thinking about the stress field in those areas, it's become abundantly clear that in most places, even in intraplate areas far from plate boundaries, the Earth's crust is sort of in a state of being critically stressed. In other words, the forces are high and pre-existing faults are close to failure. So all of these dots that we see here are just naturally occurring earthquakes that have occurred more or less in the last 50 years, as recorded by the USGS in the central and eastern United States. And basically the catalog is complete at sort of magnitude 3 and above, and you can see earthquakes have occurred nearly everywhere. In China, there's far more earthquakes in western China than eastern China, but nonetheless, when dams are built and surface reservoirs are impounded and the water pressure at depth changes by just a little bit, you sometimes get reservoir-triggered earthquakes, and that's what's shown in these red dots. So even in really stable places like the Canadian Shield, you get magnitude 4.5 earthquakes. triggered by impounding reservoirs. Eastern China, which has few earthquakes in general, but has had some very large historical earthquakes, has had a number of places where reservoirs have impounded, reservoir impoundment has triggered earthquakes, and in India as well. Very stable in general, but the faults are at this kind of point of near failure, and if you increase the fluid pressure through injection, you basically change the normal stress and allow naturally occurring earthquakes to actually occur sooner. These earthquakes would have occurred anyway at some point in geologic time, but the injection process advances the clock. Now, this is, for those of you who are not geologists, this looks a little complicated. For those of you who are, you saw this in your freshman or sophomore year. But basically, there are different kinds of styles of faulting in the Earth's crust, and there are predictable relationships between the forces in the Earth and the orientation of the faults. And I want to talk about this situation right here, what's called strike-slip faulting. If you know the force, then you expect faults to slip that are more or less vertical and strike about 30 degrees from the direction of the maximum compressive stress. The reason I'm showing you that is that this is exactly what we see in Arkansas. So there was shale gas development. The flowback water was taken to an injection well. The injection well was located right there. They started injecting. Small earthquakes started to occur. Those earthquakes started to line up along a fault which is at exactly the right orientation for strike-slip faulting to occur. So it would have been known immediately, if there was a local seismic network, that not only were the earthquakes occurring, but the earthquakes were lining up along a geologic fault that had just expected orientation for the regional stress field, which is very well defined by data that's just off to the west of this map. This location is just right about there. So textbook, very simple case, but in fact, nobody was paying any attention. The issue of triggered seismicity wasn't continued, and then nothing was done until a magnitude 4.7 occurred, and basically, came to the governor's attention, and then injection was stopped. Now, this is a manageable problem. We understand how earthquakes work. We understand why injection triggers earthquakes. And it's really simple. But you have to be proactive, and you have to think about these things ahead of time. You have to avoid injection into potentially active faults. Duh. You have to limit injection rates. In other words, you have to limit the pressure increases at depth, especially when the permeability is low. There are now 100,000 Class 2 injection wells operating around the country, 100,000, 50-some thousand in Texas alone, okay? And nothing ever happens. And the main reason is the relatively low volumes are injected into very large reservoirs. The pressure changes are insignificant. But when larger volumes are injected into less permeable rocks, the pressure goes up and you can get triggered seismicity. You have to monitor the seismicity. If there's any reason for concern, install a local network. And seismologists know how to locate earthquakes in space and time extremely well, and you can immediately know whether or not something like this is beginning to happen. And then you have to be prepared to stop. Okay? So there's never been an injection-induced earthquake that's caused injury or fatality. There's never one that's caused serious damage. But people are feeling them, and people are concerned about them, and people deserve for their concerns to be addressed, and they can be addressed by simply just being more careful in the site characterization step, and by monitoring what's going on and taking the appropriate action. And the regulators have to work with the companies to put all this in place ahead of time so that the appropriate actions can be taken. Another thing our committee talked about was managing the cumulative impacts on communities, land use, wildlife, and ecosystems. And this is something that's really falling through the cracks right now, and it's a really major issue. As shale gas development is proceeding, individual wells are being permitted, or some other, pumping station is being permitted or a pipeline is being permitted. But no one is standing back and looking at all the wells and all of the impacts. And this is a major gap, and this needs to be addressed. And our committee felt very strongly about this. So last summer, Time magazine had this on its cover. This rock could power the world. In very small print, they say there's a century's worth of gas in our backyards, but there are some environmental issues that need to be addressed. I wish the type had been bigger, okay? I actually feel that this rock will power the world, but there's still a lot of work to do, both on this side of the diagram and this. Thank you very much.
Okay, great. We have time for questions. No. Okay, let's see if students first. Okay, here, back there.
One thing that wasn't mentioned during the presentation was the danger of radiation contamination during the hydraulic fracturing process. How is it different from the dangers that you mentioned in the presentation, and how do we mitigate it?
The issue concerns the flowback water and naturally radioactive minerals that are in the shale coming back when the water is flowed back. So there were some original reports of there being a fair amount of this in some of the waters. Some of those reports were later retracted and contested. But the issue is a real one. What comes back after hydraulic fracturing presents us water that, has to be dealt with in a responsible way. The best thing to do is just re-inject it back into the shales, okay? And if you don't do that, then you have to deal with it properly. Treatment of the water is rarely done simply because it's so expensive, okay? But the stuff that's, the chemicals that are injected that have caused a lot of concern are really not the problem. The problem is what comes back out of the shales, and that could include radioactive materials as well as other contaminants. Yes?
I'm wondering, with all of the injection of the backflow water into various saline aquifers, have any studies been done as to what the various detergents and things added to that might do underground?
The question is the cumulative effect of the additives. Even if they're relatively benign, they will accumulate over time. I don't think that's been studied. It's probably something that should be looked at. The friction reducer is often compared to dishwasher soap, which most of us deal with without concern. The biocide is rather benign, but nonetheless, when these things accumulate, they could pose a danger, and that probably should be looked at more carefully than it has been. So that's a good point. Yes?
A lot has been discussed about replacing coal for baseload generation. What's your opinion on the opportunity in converting natural gas to liquids, chemicals, and fuels?
Well, the opportunity to convert natural gas to liquids is really important, because that would make its use as a transportation fuel, that much greater. The net saving for CO2 when you use natural gas for transportation is not nearly as dramatic as it is as using natural gas for electricity, but it does contribute to energy security issues and all sorts of things. And I heard a talk about 10 days ago by Marvin Odom, the president of Shale, and he addressed that directly. And Shell, like many other major companies, have been spending an awful lot of money trying to figure out how to do that. It's a very high priority. There are a number of technologies that are being investigated, and it's really a major goal for a number of energy companies to try to liquefy natural gas at an affordable price, basically so that it can be used for transportation as well as heating and electrical generation.
There's two over there. Yeah.
Is there a concern with where natural gas prices is today, or are today, that we will use the resource in a manner that doesn't fully capture the value from a firming capacity on the grid and taking long-run interest in mind?
Yeah, I often show a slide, I didn't today, on sort of the financial break-even point for natural gas for a lot of these different basins, and depending on the depth of the shale and the operating condition, the price varies from place to place. The cheapest place to produce gas, the operators need a price of about $4 per million BTU to make a profit. In other places, it has to be up around $6. The current gas price is $2.80, which means gas is so cheap that companies cannot afford to actually drill and produce it. So what you're seeing right now is such a glut of gas in the United States that companies are doing the minimum drilling to basically hold their leases. They're waiting for prices to rebound. Obviously, when if gas starts to be exported more through LNG plants, and one has been permitted now to be, a few years ago we were talking about importing gas. Now we're talking about exporting gas. So as more gas is used for electricity, more gas is exported, the prices start to come back up, the companies will start drilling again. But right now they're doing the minimum drilling they can because they're losing money on every well. So there's kind of a sweet spot between about $4 and $6 where we're cheaper than coal, but the price is high enough that the gas companies can actually afford to go out and produce it. The other problem is when prices are low, there's all these economic incentives to cut corners on well construction because that's where the money is being spent. And that's where the environmental problems occur. And so that's my biggest concern. And that's where we have to get the regulatory system in place. And the regulations are now being done by, the regulatory system is really carried out by the states. I think that's correct, but not all the states are doing a good job. And that's where the federal government steps in and tries to kind of raise the bar and help the states improve regulations, especially on drilling construction.
Okay. I think that back there,
Oh,
you were first, and then maybe we'll move up there.
All right.
Yeah.
So probably by design, there were not any industry people on the committee. And so what is the anticipated receptiveness amongst folks in the industry to your recommendations?
Well, it might surprise you to know that industry the lack of industry participation wasn't our problem. When we met with a number of environmental groups, it was argued that because 6 of the 7 of us were so contaminated by our interactions with the petroleum industry that nothing that we had to say would be of any interest to them. And they asked our chairman to resign on the spot. So we were our problem has been being viewed as shills for industry as opposed. I think the position of industry is complicated. Groups like the API, the American Petroleum Institute, which represents everybody, but the small operators have a big influence. They sometimes tend to adopt the lowest common, what everybody will agree to, which is not always the best thing. The big companies have a lot to lose, and they have a big stake in the game, and they'll always be far more conservative and far more careful. In general, our recommendations have been well received by industry because we're very supportive of the development, and the bigger companies have no problem with our 20 recommendations. The question really is whether the state regulators will follow our regulations and whether the small companies will be forced to follow them as well. And it's the implementation that our committee, we feel good about what we've recommended. Our recommendations have been well received, but our fear is if our recommendations are not implemented by the states, they're just words. And that's a great concern to us.
There was a gentleman, I think, do you want to go? With the turquoise shirt. No, sorry. Yeah.
You addressed the issue of the risk of contamination of groundwater resources, but you didn't really talk about the stress that this industry is putting on water resources and the consumptive use of those water resources. Did your recommendations include recommendations about water resource management and essentially identifying areas where probably development of natural gas extraction using this method may not be viable compared to others where their water resources are under less stress?
Yes, we did talk about that, and it kind of came into this regional planning, to look at water issues at sort of the watershed scale and to consider alternatives to freshwater use. I mean, the Eagle Ford in South Texas, the drought has really created a major problem for everyone and makes the water use associated with gas development even more more difficult. So as I pointed out, saline water can be used for hydraulic fracturing. The companies prefer not to do that because it gives them other challenges, but they can do that. And they will do that when they have no choice. And so I didn't talk about it, but one of the bullets was called organizing for best practice. What organizing for best practice means was to get local communities, regulators, and companies together to try to address those issues of how to plan the development more than a well at a time or a pad at a time, how to develop the resource while making the best decisions possible about water use. One of the interesting things is that when gas development begins, you have an incremental need for more water. When you actually look at the total energy system, natural gas development uses a lot less water than burning coal for electricity. So the net is good, but the increment is bad, and in some places the increment can't be sustained because of just existing conditions, in which case industry has to be a bit more clever about what it does.
Okay, maybe we'll take just one more, and I think, Mark, you had your hand up. Yeah.
Yeah, it's recently it was announced that Shell and CNPC found or extracted the first gas from shale in China, and that could be a big game changer if China's resources are developed. Do you have a good sense of what some of the geological similarities and differences are? I mean, are there particular challenges that are likely to be unique to China?
Well, one of the sort of cliches of working in the shale gas arena these days is that every shale is different, and I think there's no reason to suspect that it won't be true in China as well. For example, if they tend to be more like the Floyd Shale, the same amount of organic material, the same maturity, everything's great, but there's just so much clay in them that they can't be exploited. It could pose major challenges, and that's true in places like Poland and Argentina. So basically, it's just going to take some time. People are going to have to drill some wells and find out what works and find out what doesn't and why. And there may well be some of these shales that turn out to be unproductive. The gas is there, but it just can't be unlocked using this technology, and people will try alternatives.
Okay, with that, I think we need to thank our speaker.
For more, please visit us at stanford.edu.